So for that, the we can see that the processing is required, which is a normalization, and then we go for associate formula, and then we will rank all the solutions, and then we will select the required number of solutions from the solution that is already present in front L. Okay. So this is the NSTA flow. Now let's go each and every step in detail and very briefly. Now here you can see that X is nothing but a solution set. We have some constraints, and F1 to Fm is nothing but a objective function. M is nothing but the total number of objective function. Okay. Now this is a non-dominating sorting method. Now just to understand you that what how the things are working, so basically I told you that here in black box, these are the black box. Okay, so this black box are ran, assume that this is M is equal to 2, which is nothing but a 2 objective space, assume like that. Okay, now here the solutions are randomly placed in this two objective space. Okay, now what we are doing, we now we divide this entire solution into different fronts. Okay, so how this is from, like, solution 1 is in front 1, solution 2 and 3. You can see the same symbol belongs to same front. So solution 2 and 3 are in second front, and solution 4 and 5 in third front. Now you guys can think that how we have divided this entire solution into different fronts. I'll tell you in detail. But before that, try to understand that this the front 1 is more dominating as compared to front 2, and front 2 is more dominating than compared to front 3. Okay, so solution that belongs to front 1 dominates the solution that belongs to front 2. But here, because solution 2 and 3 are the same front, we can say that they are non-dominated to each other. Okay, so what is the meaning of non-dominating? So non-dominating means is, let's check that we are solving this minimization problem. Now here just focus on solution 2. Okay, solution 2. Now here you can see that the solution 2 is minimum as compared to solution 3, means it is best in objective 1. However, solution 3 is best as compared to solution 2 in objective 2, right? So solution 1 is best in one objective, and solution 3 is best in another objective. So when such situation comes, so at that time we say that they are non-dominated to each other. Okay, and here when I'm saying that solution 1 dominates solution 2 or solution 3, it means that you can see that solution 1 is minimum in objective 1 as compared to, let's suppose we compare to solution 2. Okay, so here you can see that solution 1 and solution 2 are same in objective 1, but here you can see that solution 1 is less than or minimum or best than solution 2 in objective 2. So that means that solution 1 dominates solution 2, right? Okay, now we will understand more detail. Okay, so I'll tell you the combination of domination count after this. Okay, now uh, here this is the same graph which I have demonstrated in the previous slide. Now let's understand and rank the objective. Now here solution 1, you can see that. So here solution 1, we will check that whether it's dominate solution 2. So yes, it's dominate solution 2. We have already checked. Let's check whether it dominates solution 3. So yes, it's dominates solution 3. Whether it dominates solution 4, yes. Whether it's dominates solution 5, yes. So here we will keep on list down all the things. So here you can see that solution 1 is dominating all the rest solutions. So this is the set we have created. Now do solution 1 non-dominated to each other? Like, is there any other solution? So no, solution 1 is the best solution as compared to all the solution. Now let's come to the solution 2. So we'll keep on, listing or reporting for all the solution one by one. Now we come to solution 2. Now we know that solution 2 dominates solution 4 and solution 5. So here you can see that solution 2 dominates solution 4 and 5, but you can see that solution 2 non-dominate solution 3, and solution 1 dominates solution 2. So everything we need to write likewise. Same for solution 3 we have written, same for solution 4 we have written, and same for solution 5 we have written. You can, here is the, you can just take a screenshot or take a photographs and you can find by your own. So here likewise we have listed all the solutions which are dominates a particular or the targeted solution, which are non-dominate target solution, or by which solution dominates a target solution. So all these things we write likewise. Okay, now here you can now what is domination count. Okay, that now we need to think. Now domination count, you can see that which solution or how many solution dominate a particular solution. Like for example, solution 1, how many solution dominate solution, means how many solution are best than solution 1. No solution is best than solution 1. So here the domination count will be 0. Now let's come to the solution 2. How many solution dominates the solution 1? So here the solution 1, which is only one solution, dominates solution 2. So here the domination count will be 1. How many solution dominate solution 3? So only one solution dominates 3. Like solution 1 only dominates solution 3. Okay. So that's the reason why this is 1. Now solution 4. How many solution dominate solution 4? So there are two solutions, solution 1 and solution 4 dominate solution 4. So that's the reason why here domination count of solution 4 is 2. How many solution dominate solution 5? So here you can find the 3, 1, 2, 3. So the domination count of solution 5 is 3. Now what we'll do, we will rank this particular solution. Now rank is nothing but the domination count plus 1. Okay. So the rank of solution 1 will be 1. The rank of solution 2, this is nothing but a front. Okay. So the rank of, like, which front this particular solution should move. Okay. Or rank, I can say that. So solution 1 is should have rank 1. Solution 2 should have rank 2, 1 plus 1. Okay. Solution 3 should have rank 2. Solution 4 should have rank 3, and solution 5 should have rank 4. So likewise we divide this entire what we can say the solution by giving the rank. Okay. Yes, so this is how we divide this entire solution into different fronts based on the solution, as well as try to understand that solution that belongs to the same front should be non-dominated. Like here, solution 4 non-dominates to solution 5, solution 2 non-dominates to solution 5, likewise. Okay. So the theory, also the mathematical concept which I have described in the previous slide, that is described in the paper in this format, where you can see that we keeps on counting the domination count, and the rank is nothing but the domination count plus 1. You can see that. Okay, here. So rank is nothing but the domination count plus 1, and based on that, we will, we will uh, move this particular solution, into a particular front. Yes. Okay. So I come back to my original algorithm. Now here, now where we are, basically we have prepared the RT. Okay, line number 3. We have divided this solution into different fronts, which is line number 4. Okay. And also assume that we have assigned all this, like this one, particular one. Sorry. Yes. Now assume that we have given the solution of front 1 and 2, and now what we are doing, we are selecting the optimum solution of the last front. Okay. Optimum solution of the last front. So for that, we are going to use this particular formula, which is nothing but uh, associate method. We are replacing crowding method, crowding distance method. For that, we need to do some pre-processing. Now what exactly we do in pre-processing? Okay, now you know that I have given you the example of train ticket. Now in that, I hope that you remember that we have used the two objective, which is what, minimizing the time and minimizing the cost. Now the cost and the time is having the different units, right? So what we do is, whenever we are uh, manipulating or trying to extract any information with different units parameter, we first of all normalize that thing. Okay, normalize into a uniform scale. Got it? Now, for that reason, as I given the example, cost and time, they have different units. So how to deal with that type of objective? So what we do, we normalize the scale of each objective, which is 0 to 1. Okay, so here 0 to 1. So for that reason, this normalized procedure has been introduced. Now this is very simple method. This looks like complicated, but just you can see in equation 1 that this is what we are using. Now here z max is nothing but a intercept. Okay, intercept means, in mathematically concept, we can say that the maximum value at that particular objective scale. Like for example, 0 to 10. Okay, suppose for example, the price of any fruit range from 0 to 10. So 10 is nothing but the intercept value. Okay, so here you can see that compute intercept is nothing, line number 6 is nothing but a maximum value of that particular objective. Now I'll go step by step. uh, okay, so what we are doing is, we first of all normalizing the scale of each objective using this formula. So for that, first we calculate the intercept, which is z max. You can find over here in the denominator side, and z mean is nothing but the minimum value of that particular objective. Now each solution we subtract from the minimum value of the scale and then divide with the maximum value of the scale. So each solution we will normalize in that way so that it range from 0 to 1. I hope that this is clear. If you want me to go in this particular algorithm, so this is nothing but a minimum value of a particular objective, which is line number 2. Then we are translating this objective. Translating is nothing but we are shifting it. So how we can do that? So we are subtracting from the minimum value of that objective from the current value. Then we find the extreme value, which is nothing but the maximum value, it's the intercept value. Okay, now we normalize this using the below. This equation 5 is nothing but the formula which I have demonstrated over here. Now this is how this particular zs will be assigned to a particular solution. So this is how we are normalizing these solutions in the many objective space. Here for loop is assigned for that, the same process we do for all the objectives. Okay, 1 to m. Okay, so this is nothing but the objective. Now let's move to the main algorithm or the main module of NSGA 3, which is nothing but the associate method. Now just try to understand what we are doing. First, this is very important, that what is this associate method. Now just understand, see, many objective is always greater than 3 objective, but to visualize you that how the things are working, here the graph is demonstrated in 3D with the 3 objective. Okay, now what exactly we are doing is, now understand this triangle is nothing but the solution, the what we can say, the spread of the solution in 3D diagram, in 3D objective. Okay, in three, yeah, I can say there's a three-dimensional space. Now what we are doing, what we are targeting, now our target is to select the optimum solution that belongs in the last round. Okay, so here you can see this um, solid circle, which is nothing but the solution of the last round. Okay, now we need to select the optimum solution. Now how we do that? So for that, what you can see, this dash line, this is known as reference line. Okay, so this reference line, from this reference line, those solutions are nearer, we will select those solutions into the next generation. Why? I'll tell you. Because it will give you a separate the separate what we can say, the separate optimal solution. Okay, now why we need the different solutions? Because, for example, again, let's take the train ticket number, sorry, train ticket objective space. Suppose if all the solutions will give the same solutions, like you have the 10 solution, but all are saying that this is the there is only one ticket number. Or for example, you are finding the restaurant, sorry, hotel, while visiting any new places. Okay, if your Trivago or other app shows only one restaurant, then this app is not useful for you. You need to know the variety of the solutions when you are targeting the different objective, that number of large facilities which we consider as an objective. Okay, so we don't want overlapping solutions, we want the separate, that is the separation in the optimum solution, and all the solutions should be non-dominated to each other, right? One is better than the one is better in one objective, another better in another objective, but they are optimum solution. This is what the real time requirement is from the optimization algorithm. So this is the case what we are also doing over here. We are trying, the reference line will help us that the optimum solutions don't overlap. For that we are designing this reference line. Now how we will get this reference line? Do I have time? Yes. Okay, now how will I get the reference line? So what we are doing, we are first of all selecting the reference point in this 3D space. How to calculate that, I will tell you. Okay, now we will select this reference point. Can you see this circle over here, the gray circle, empty circle, right? So these are the reference point. Don't worry, I'll tell you how this came. These are the reference point. When we connect the origin from origin, when we draw a line from origin to a reference point, okay, this becomes a reference line. So to draw a reference line, we need first of all reference point. I think that this is clear to you. Now once we do, now why we are doing this, let's understand that also, so that it will be interesting for you to find out the reference point as well. Okay, now when we are drawing this reference line, now you can see that all the reference lines are drawn into this 3D space. Now what we are calculating, we are calculating the similarity, or we can say the minimum distance, or the distance from the reference point. Can you see this? The line has been drawn, which this line shows that this is a Euclidean distance we are calculating, right? So this line will shows the similarity or the distance between the reference line from the point. So those, then we will, okay, we will calculate all the distance, like for, we will calculate the distance for this particular reference point, sorry, this particular solution from the reference line, this particular solution, this particular solution. So we will calculate all the distance, then we will sort into an ascending order, and those are nearer, which the nearer solution will come to the upper block, and then we will like for example, we want to choose only two solutions from the last one, so we will choose that into the next generation. So this is what all the target is, or the goal is. Now to come to that solution, what we are doing is, we are, okay, we are calculating the reference point. Okay, now how to calculate the reference point? So can you see this? Just focus on this x-axis side. Okay, don't focus on this 3D space. So you can see that the division. Now it's your point. Okay, that how much division you want. Okay, in this example, I have chosen the 4 division. Okay, now 4 division is 1, 2, 3, 4. So I want that each objective should be divided into 4 sections. Okay. Now how many objective I have? I have 3 objective. Okay. So 4 division, 3 objective. Now you need to know that by doing this, how many reference points will be created. So this is the formula, which is nothing but m plus p minus 1 cp. Okay, so when we assign this value, m is equal to 3 plus 4 division. Again, I'm saying 4 division is this 1, 2, just focus on my cursor. 1, 2, 3, 4. We want to divide our each objective into 4 section. 1, 2, 3, 4. So p is equal to 4. Okay. Now here m plus p is nothing but what? 3 plus 4, 7 minus 1, 6 C 4, which is nothing but 6 C2. 6 5 is a 30 divided by 2, which is nothing but 15. I hope that you understand. Okay. So by using this formula, it is came that there are by dividing the each objective into 4 section, 15 reference points will be generated. I'll prove that how it will be generated. Now this is the method. Okay, now you know that we have used the normalization method so that we can divide this entire scale into 0 to 1 range. Okay, now we have decided that like each objective we will divide into 4 section. Okay, so when we are doing 1 divided by 4, so each subsection comes the range is 0 to 0.25. Okay, the difference is 0 to 25. So when we are dividing 0 to 1, so the point will come as 0, 0.25, and then plus 25 करेंगे तो what will come 0.5, then again we'll do plus 25, then 0.75, again we will do on this plus 0.25, then it will come as 1. Okay, so this we did. Right, now what we'll do now, to this is our one objective. Okay, we are interested in 3 objective, so we will move into a different objective. Okay, now what we'll do, we will minus this particular value from 1. So 1 minus 0 is 1. So again, we have to follow from 0 to 1. The same process what we did over here. So here you can see that 0, 0 0.25, 0 0.5, 0 0.75, 1. Okay, now let's see this 0 0.25. Okay, now we will subtract this from 1. So 1 minus 0 0.25 is what? 1 minus 0 0.25 is 0 0.75. So we will do this entire process from 0 to 0 0.75. 0, 0 0.25, 0 0.5 and 0 0.75. Now let's come to this 0 0.5. Subtract this from 1. 1 minus 0 0.5, which is nothing but 0 0.5. We will do this entire process till 0 0.5. So you can see that 0, 0 0.25, 0 0.5. Next 0 0.75. So 1 minus 0 0.75 is nothing but 0 0.25. We will do this entire process till 0 0.5. So you can see that 0, 0 0.2 is 1. So 1 minus 1, which is 0. So we will just be there 0. So this entire value is nothing but a second objective. Now we want to move to the third objective. So we don't need to do again and again because we need to stop at third objective. So when you are at last objective, then you need to do only the summation part. Okay. So just the summation of each point should be 1. Just understand this. Summation of each point should be 1. Then you will get the reference point. So 0 plus 0 is 0. So to make it 1, we need to add 1. So here you can see that 1 is added. 0 plus 0 0.25. To make it 1, we need to add 0.75. 0 plus 0.5 is equal to 0.5. So to get the 1, we need to add 0.5. 0 plus 0.75 is equal to 0.75. So to make it 1, we need to add 0.25. 0 plus 1 is equal to 1. So to make it 1, it is already 1. So we will add only 0. For this skill, again I'm repeating so that if anybody is missing, so they can catch. 0.25 plus 0 is equal to 0.25. To make it 1, we will add 0.75. 0.25 plus 0.25 is 0.5. To make it 1, we will add 0.5. 0.25 plus 0.5 is nothing but 0.75. To make it 1, we will add 0.25. 0.25 plus 0.75 is equal to 1. To make it 1, we will add 0. Okay, because 0.25 plus 0.75 is equal to 1. Okay. Now 0.5 plus 0 is nothing but 0.5. So to make it 1, we will add what? 0.25. 0.5 plus 0.25 is 0.75. To make it 1, we will add 0.25. 0.5 plus 0.5 is equal to 1. So we will add 0. Similarly, we'll do for 0.75 as well. So 0.75 plus 0 is nothing but 0.75. So we'll add 0.25. 0.75 plus 0.25, we will add 0 because this becomes 1. 1 plus 0 is 1. So we will add 0. Clear? I hope that this should be clear. Now we will start writing the points. Okay, now this is the reference point. Now the first reference point is, because this is a 3D space, try to understand that this is a 3D space. Okay, F1, F2 and F3. So each solution will represent the three objective value, like F1, F2 and F3, right? Okay, so here we will write 0, 0, 1. So this will be our first reference point. 0, 0.25, 0.5. So 0, 0.25, 0.75. So this is our second reference point. 0, 0.5, 0.5. This is our third reference point. So this is how you keep on, keep noting all the values and keep writing in this way. Okay, so when you will count it, you can see that in the first column you can find this 5. First column is like, basically from this particular branch we are getting this 5 reference point. From this particular branch we are getting the 4 reference point. From this particular branch we are getting the 3 reference point. From this particular branch we are getting the 2 reference points, and from this we are getting the 1 reference point. That's the reason why this is arranged likewise. So here you can see that 5 plus 4 is nothing but 9. 9 plus 3 is 12. 12 plus 2 is 14, and plus 1 is 15. So in the so this formula which I was telling you, which is nothing but the 64, which is equal to 15. So here hence prove that by dividing, so using this formula and by using this technique, you will be able to generate the reference point. Just plot this particular reference point in the 3D space. So you will get this particular reference point in this particular space. Can you see this gray circle? Okay, so when you plot this reference point, you can find like this. Now to draw a line, from the origin of this objective space, draw a line to this particular reference point. So this becomes a reference line. Okay, so I have still time, 10 minutes, right? Now let's quickly come to the associate procedure. So what I have already told you that once you draw a reference point, like you can see that in line number 1, for each reference point, we will calculate a reference line. Okay, now from the reference line, we will calculate the Euclidean distance. Can you see the sign over here? Perpendicular distance. So we will calculate the Euclidean distance, and those, can you see this argument minimum? It means that those minimum distance solution will move into the next iteration. So this is all about associate procedure and the NSGA3. We are just replacing the crowding distance module to a associate procedure into the NSGA3, which makes the NSGA2 to NSGA3. Okay, so these are basically the I can say the research papers that me and Nanda sir and one of our senior Urvashi madam, we combined uh, collaboratively written some good papers. You can go through our Google Scholar account and visit that how the process or the approach we have followed to develop the algorithm. Now, Nanda sir specially told me that to you guys, I showcase some of my like the application basically. Um, yeah, the applications of the same. So basically, as I told you that, um, I have actually planned to showcase you that. Just a second. So here I am. So I have planned to showcase you the application, but before I start demonstrating you, so this application is from my PhD research work. Yeah. So basically, you can use this a many objective optimization algorithm into multiple. I can say that. Multiple application like Trivago is a very good applications where it is satisfying the what I can say the multiple objective space to get the optimum hotel details to you. So these are the many applications, but we have applied it for I can say that for the satellite images. If I have that, yeah, okay. So what we in our like in my thesis, what I was trying, just allow me 2 minutes. I'll just give you. So in my PhD duration, me and Nanda sir was working with the satellite image processing where we have converted this particular NSGA3 algorithm into the clustering algorithm. Okay. And then we have applied over these satellite images and divide that entire, satellite image into different Earth surfaces, and we have also developed the modified version of NSGA3, which is the theta NSGA3. Uh, so over there, we observed that our results were coming comparatively better than the result what we see over here using the NSGA3. But NSGA3 undoubtedly it is working wonderful way. Yes. Okay. I was actually trying to show you that what exactly we did, but I failed to find the application related presentation. Again, I'm checking that if I can showcase you the same by any chance. I think I'm good. If you have any question, you can ask me simultaneously.
Hello, Dr. Rachna. Yes, I suggest all the participants to put queries in the chat box.
Okay.
So you can have a look that there is a chat box over here.
I can see the chat box, sir, but
Yeah. People will put questions
okay.
in that one. Okay.
I think.
Eh, It was really a nice presentation. You have explained all the steps of the NSGA 3 algorithm in a perfect manner, step by step wise. So, if people will follow the Professor Kalyan Mahadeev's paper and your explanation on it, it will be easier for them to understand the many objective optimization problem. So, I request you to share your slides so that it can be shared with the participants.
Sure, sure, definitely.
Yeah. So, if you can wait for just a
Yeah,
couple of
definitely.
minutes, people used to
Sure, sure, sir.
take little time to put up questions. You can look at there are almost 170 participants are listening to you. Yeah.
Yes. How should I know the solution one is better comparing all of the solution based on slide number 10? Okay, let's go to the slide number one. Again, I'm sharing my screen.
Uh,
Uh,
Without sharing, also you can just able to explain. No.
okay, fine. So, how the solution one is better comparing all of the solutions? Okay, so solution one. So this is asked by Raja Sekar. Okay, so Raja Shekhar, because as you know that we have plotted that particular solution into two objective space. Okay, so this solution one was, and we were first of all solving the minimization problem. So this particular solution was minimum in objective one and in objective two also, as compared to all the solution that has been plotted into that two-dimensional space. Okay, so based on that, we concluded that because it's a minimum solution in both the objective space, the solution one is better than all the solutions, and that's the reason why solution one dominates all the solution which is present in the two-dimensional space. I hope that this is clear. You can answer me over here. Sorry for this background noise if it is coming. Okay, solution one and solution. I think that I should share my screen quickly. 1 second. Okay, so what has been asked? Solution one and solution three is in the same line. I just see that. Okay. Mm, Solution two and solution three were in the same line. Okay, I'll show you.
Yeah.
Can you see this? Solution 2 and solution 3 were in the same line, and we have also discussed that solution 2 and solution 3 non-dominates each other. Can you see this? Solution 1, which is minimum in both the objective space, and solution 2 and solution 3 are in the same line. Okay, you are saying that this way. Solution 3 and solution 1 for the second objective is in the same line, but you can see that for objective 1, solution is minimum as compared to solution 3. Again, I'm saying we are considering that it's a minimization problem. And that's the reason why solution 1 is better than solution 3. Okay. Although I'll share this slide, with you via Nanda sir, so that I'm sure that if you go thoroughly with this slide, you will definitely get the idea of NSGA 3. And those who knows the NSGA 2, it is very very easy for them to understand the NSGA 3, because we are only replacing a single module, which is nothing but a crowding distance method to a associate operator. That's it. And the idea is to get the more optimum solutions from that non-dominated front. Okay, so that's the reason why we are using the reference point and reference line concept, and find out the minimum distance from the reference line solution from the last friend. This is the all concept in NSGA 3.
So thank you, Dr. Rachna.
Okay sir,
Okay.
thank you sir. I'm just closing.
Yeah, thank you.